không.
Experiment 1 is the forensic luminol experiment. The materials we need to prepare are luminol powder, 1 gram, sodium hydroxide 10%, or solid 5 grams, to create an alkaline medium, hydrogen peroxide 3%, household peroxide, oxidizing agent, from 5 milliliters to 10 milliliters, potassium ferricyanide crystals source of Fe plus catalyst, distilled water, 100 milliliters. First, I will add 0.5 grams of sodium hydroxide to the spray bottle containing distilled water, then shake well. Next, add the whey luminol, 1 gram, into the spray bottle and shake well until it is completely dissolved. And with that, we have prepared the luminol solution. Now, let's try using the prepared solution on the following mock crime scene.
Hello everyone, I am crime scene investigator Thủy Tiến. I'm currently at the scene of a homicide. At first glance, this place looks clean, but is it really? Let's check it out together. Oh my god, do you see that? Tracks of blue light are appearing. That means there were blue here. I will investigate and give you more information later. Goodbye and see you again.
Phenomenon. Mix luminol in base with hydrogen peroxide and sprinkle potassium ferricyanide. An intense blue light appears without heat, then fades over time. Explanation. Luminol is oxidized by hydrogen peroxide in alkaline solution, with Fe3+ as a catalyst, analogous to the iron in hemoglobin. The resulting 3-aminophthalate in an excited state emits a photon as it relaxes to the ground state chemiluminescence.
Red cabbage leaves. 5-10 grams, as a natural source of anthocyanins. Hot distilled water, 70-90 degrees Celsius, approximately 100 milliliters for pigment extraction. Acidic solutions. 0.1 m hydrogen sulfate, pH approximately equals 1. 0.01 m HCl, pH approximately equals 2. Neutral solution. Distilled water, pH approximately equals 6-7. Basic solutions. 0.1 m sodium hydrogen carbonate, pH approximately equals 8-9. 0.1 m NaOH, pH approximately equals 12-13. 5 clean test tubes for comparison. When red cabbage leaves are placed in hot water, they release a deep purple extract rich in anthocyanin pigments. Then, gently add this extract into test tubes containing acidic, neutral, and basic solutions, from hydrogen sulfate and HCl, to distilled water, sodium hydrogen carbonate, and NaOH. Watch carefully as the colors shift beautifully with changing pH levels. We can visualize the pH change through a neutralization process, starting from a basic solution of pH 12, slowly adding acid until it turns strongly acidic at pH 1. Observed phenomena. When the red cabbage extract is added to solutions of different pH values, the color changes distinctly. Strong acids, hydrogen sulfate, HCl, right pointing arrow bright red. Neutral medium, distilled water, right pointing arrow violet, purple. Weak base, sodium hydrogen carbonate, right pointing arrow blue or greenish blue. Strong base, NaOH, right pointing arrow yellowish brown. Explanation. Anthocyanin is a flavonoid pigment with an extended pi conjugated system, highly sensitive to pH variation. At low pH, it exists mainly as the flavolium cation, red form, a stable, fully protonated structure with strong conjugation. As pH increases, the molecule loses protons and gradually shifts to quinonoidal base forms. Violet right pointing arrow blue, altering its electronic transitions. At high pH, the flavolium ring opens, forming chalcone species, yellow, brown, due to loss of conjugation. Right pointing arrow thus, pH directly affects the protonation state and the degree of pi electron delocalization, which in turn determines the observed color of the anthocyanin solution.
For this demonstration, we will use liquid potassium permanganate as a purple oxidizing agent, 3% hydrogen peroxide as the reducing agent that will generate oxygen gas, and a small amount of soap or dishwashing liquid, about 2 to 5 milliliters, to trap that oxygen in the form of foam. We will also add sodium hydroxide to create the alkaline medium needed for the reaction, and we'll use distilled water to dilute and prepare the solutions. About phenomenon in sodium hydroxide medium. The purple color of potassium permanganate gradually disappears, and the solution or foam becomes dark brown. A fine brown precipitate of manganese 4 oxide appears, remaining suspended and coating the foam films. A large amount of bubbles is produced because hydrogen peroxide decomposes to oxygen. The soap stabilizes these bubbles, so a brown foam column rises. About explanation. In an alkaline medium provided by sodium hydroxide, hydrogen peroxide reduces permanganate ions manganese in oxidation state +7 to solid manganese 4 oxide dark brown, while the hydrogen peroxide itself is oxidized to oxygen gas. The soap does not take part in the redox reaction. It only stabilizes the oxygen bubbles, which makes the brown foam column easy to observe. For this experiment, we will use a cobalt sulfate solution at about 0.1 to 0.5 m and an ammonium carbonate solution at about 0.5 to 1 m. We also need a transparent Petra dish and a dropper, and underneath the dish we place a sheet of paper with a drawing of a tree trunk and branches. This setup will let us grow the colored precipitate right along the shape of the tree. About observed phenomena. When drops of cobalt sulfate solution are added to the ammonium carbonate solution, a pink-purple precipitate appears almost immediately. Instead of sinking, the solid spreads across the surface and grows into thin, branching patterns, making it look like a miniature chemical tree. About explanation. Cobalt-2 ions from the cobalt to sulfate react with carbonate ions from ammonium carbonate to form a sparingly soluble solid, cobalt to carbonate. The first precipitate layer behaves like a porous barrier, so ions can pass through only at certain points. At those points the reaction continues and the precipitate grows outward, producing leaf or branch-like crystalline patterns.
The experiment, silver tree on copper, demonstrates a single displacement reaction between silver nitrate and copper metal. For this activity, we'll need a silver nitrate solution with a concentration of about 0.02 to 0.05 molar, distilled water, and a clean piece of copper wire or copper strip. First, take a copper wire that has been bent into the shape of a small tree, and place it gently into a clean beaker. Then, pour in the 0.05 m silver nitrate solution, silver 1 nitrate, until the wire is completely submerged. Let the setup stand still for a while, and observe carefully. Phenomenon. Immersing a clean copper wire or strip in a dilute silver 1 nitrate solution causes the copper surface to quickly become coated with silver crystals, gray or silvery, often forming fern-like or snowflake-like dendrites. Explanation. A displacement, redox, reaction occurs. Ag ions are reduced by copper to form metallic silver that deposits on the surface, while Cu is oxidized to Cu ions, turning the solution blue.
Liesegang rings, periodic, precipitation pattern in gel. The materials we need to prepare are silver nitrate solution agno, approximately 0.1 m, potassium dichromate solution K-grows, approximately 0.1 m, pure gelatin analytical or food grade, clean glass test tubes, distilled water. Procedure. Dissolve 1 to 2 grams of gelatin in 50 milliliters of hot water around 60 degrees Celsius. When the gelatin is dissolved, add a very small amount of few crystals, about 0.05 grams polydichromate, and stir well. The gel solution will now have a pale yellow color. Pour this yellow gel solution into a test tube about 2/3 full. Important, place the test tube in a refrigerator or a cool place until the gel has completely set like jelly. After the gel has set, pour about 2 to 3 milliliters of Agno 3 solution 0.5 m1 m onto the surface of the gel. Seal the mouth of the test tube and place it in a rack in a quiet, undisturbed location, away from light. Observed phenomena at the interface between the agno solution and the cacao-containing gel, a thin reddish-brown precipitate of silver chromate agcro forms almost immediately. After a few hours, a series of concentric reddish-brown rings appear progressively deeper within the gel, separated by clear, transparent zones. These evenly spaced bands form a periodic pattern, known as the Liesegang rings. Explanation: although cacrose is used in the neutral gelatin medium, the equilibrium shifts to the left, producing mainly chromate ions Cro squared. When agno is added on top of the gel, ag ions diffuse downward and react with Cro squared ions, forming reddish-brown ag-Cro precipitate. When the ionic product exceeds Ksp, the first precipitate layer acts as a diffusion barrier, creating clear zones. As ag continues to diffuse, new precipitation zones appear, forming periodic Liesegang rings of ag-Cro in the gel.